your host, Nick Jikomis, and today I'm speaking with Dr. Ronald Krauss. Dr. Krauss is a physician and a medical researcher. He's professor of pediatrics and medicine at the University of California, San Francisco, and his research focuses a lot on plasma lipoproteins and related traits that influence cardiovascular health and disease. So he thinks a lot about diet and nutrition, the effects of diet and lifestyle on cardiovascular health, things like dietary fats, so saturated versus unsaturated fats, carbohydrates, how all of these things influence our physiology and our health. So things like blood lipid levels, cholesterol levels, cardiovascular disease risk. And we talked about a lot of topics in this realm. We discussed how some of the major ideas that influenced dietary guidelines came about and evolved over the past several decades. We talked about the so-called diet heart hypothesis, which is an influential hypothesis that was formulated many decades ago that basically said, saturated fat was linked to cardiovascular disease. And so that led to the guidelines that said you should reduce saturated fat intake, increase carbohydrate intake. We talked about the process by which these guidelines are actually set and why Dr. Krauss doesn't think the current dietary guidelines around fats is actually a good reflection of what the literature actually states. And, we got into a discussion of a lot of the relevant science here. So what is the relationship between dietary saturated fat, dietary cholesterol intake, and HDL and LDL cholesterol levels? How does diet, including fat levels and carbohydrate intake, how do those things actually affect our health and our disease risk? We talked about the difference between saturated and unsaturated fats, some about how they work in the body, how different types of dietary patterns influence things related to cardiovascular health. So if you're interested in diet and nutrition, in particular how they relate to things like cardiovascular and metabolic health, things like saturated fat and cholesterol, this is a really good episode. We covered a lot of ground. This episode is supported in part by Athletic Greens. Their main product, AG1, is a comprehensive and convenient daily nutrition product containing 75 vitamins, minerals, and whole food sourced ingredients with less than 1 gram of sugar per serving, no nasty chemicals or artificial anything. It's gluten and dairy free and compatible with paleo, vegan, vegetarian, and ketogenic diets. AG1 is a quick and convenient way to supplement your diet to help ensure your body is getting the nutrients it needs. It comes in powder form and you can mix it in water and drink it, or you can put it into a smoothie or a shake or something like that. I mix it into water and drink it with the first meal of each day, and it's super convenient. If you go to athleticgreens.com/mindandmatter, Athletic Greens will give you a free 1-year supply of vitamin D and 5 free travel packs with your first purchase. Their vitamin D product comes in tincture form, so you just take 1 drop each day. A large fraction of the population is actually vitamin D deficient, especially in winter months when we get less sun exposure. And vitamin D is super important for the proper function of the immune system and for a variety of other things. And there's even evidence indicating that vitamin D deficiency is correlated with more severe cases of COVID-19 in those who get infected. Every time I go into the doctor each year for a checkup, I'm always told that vitamin D deficiency is very common and I should be supplementing on a daily basis. So visit athleticgreens.com/mindandmatter or click the link in the episode description. You'll get a free 1-year supply of vitamin D with your first purchase. And with that, here's my conversation with Dr. Ronald Krauss. To start off with and get us talking about some of this stuff is what did you have for breakfast this morning?
Well, I do have maybe an ounce or less of orange juice to get started. Then I have cereal, which is it's called Fiber One. It's pure fiber with no sugar, and I put fruit on it and some nuts. I have a mix of fruits: blackberry, blueberry, strawberry, and raspberry. So it's a colorful mix of fruits. I sprinkle some cinnamon on it. Have some milk, which is, by the way, not full-fat milk, and coffee, and half a bagel with a bit of butter.
And is that something you've always eaten, or is that how intentional is that breakfast given who you are and what you study?
It's totally intentional, and I do this breakfast usually three times a week, alternating with breakfast where I have a single egg. with bagel. Oh, I also have melon, as part of my food quota. So no, I do the cereal and the fruits intentionally. Oh, and banana. I forgot about. I had a banana. So it's really a mix of everything I know how to use that might have some nutritional health benefits, and that's how I drive my breakfast.
And so, why is that your breakfast? What are some of the key? What's sort of the macronutrient profile there that you're
Okay.
aiming for?
Well, I don't. Well, let me just say at the outset, I don't really try to hit a specific set of numbers. I'm although I'm number oriented and very data centric in my research. I don't feel that using percent distribution of calories for the macronutrients is all that helpful. I just think we should be thinking about food composition over overall dietary patterns. And what has been shown is that once you've picked the right foods and the right dietary patterns, the macronutrient distribution takes care of itself.
Mm.
Um, you don't start there. You can end there if you want. But where I start is getting to your question. With the fiber cereal, because I think we in general don't get enough true fiber, and there's a real issue which we may talk about perhaps today regarding the types of carbohydrate and whether carbohydrate is good, bad, or indifferent, and that depends a lot on the way the carbohydrates are prepared. So I choose the cereal, and I don't have a disclosure here. I just found that this particular brand, Fiber One, has a very high quota of true fiber, unprocessed carbohydrate, and no sugar. So that forms the core. And on that, I just, as I was saying, I just take all the plant-based nutrients that I can acquire, the phytochemicals that we get from these variety of fruits, and include that just as a basic component of a healthful diet, which again most people don't get enough fruits and vegetables. So I really focus very heavily on those aspects, and it extends into dinner as well, where I usually have several different vegetables at once, and occasionally some fruits. So that's really the driving force, is both choosing carbohydrate, because I do like carbohydrate, but I want to be careful in the type of carbohydrate I eat. I've been very much involved with reducing carbs in the overall diet as a means of improving metabolic health, particularly for individuals who may be at risk for heart disease and diabetes. But carbohydrates from the right sources can contain the nutrients as well as fiber, and so that's something I'm focused on as much as anything else.
Mm-hmm. And when we think about carbohydrates, one thing people talk about is just overall amount of carbohydrates someone consumes. But there's different types of carbohydrates. What are some of the major different types of carbohydrates that are out there?
Well, carbohydrate, as with many of our other nutrients, can be extremely complex chemically, with many, many different forms that arise from different sources. But the major categories that I think about to try to sort of simplify that start unprocessed carbohydrates at the top of the list of priorities, where there has been no grinding up of the external capsule, and they're usually dark rather than light, and that source of fiber has been shown to have health benefits both in the GI tract and perhaps in metabolic conditions as well. And a lot of that is also called insoluble fiber, because there's a second category of carbohydrate foods with fiber that is soluble. So soluble carbohydrate is a second category. Soluble fiber is a second category. And that comes from foods such as oatmeal, which I, by the way, eat periodically, substituting it for the fiber cereal. And it can be taken even as supplements. I've used some patients who have cholesterol problems. Soluble fiber has been shown to reduce cholesterol. So that's found, as I mentioned, in oatmeal, but there's other sources as well. It's commercially available in a form called psyllium. Then one moves from those two categories of healthy carbohydrates to ones that get progressively more problematic. And at least potentially problematic as the carbohydrates get processed, to remove the outer shell, the capsule where a lot of the fiber is contained, and you then get white starches, white rice, pastas, potatoes. Again, the ones that are white have been more processed, and they tend to have effects that can aggravate metabolic traits that we're concerned about. They're not unhealthy, but they just don't have the best properties to them. And then one moves to, and I'm trying to simplify this as much as possible, sort of the bottom of the list are carbohydrates that are simple sugars, which are a completely different category, but are considered as part of carbohydrate intake because they're contained both within foods that we select, even from some of the healthy foods, but also have. I should mention I also eat low-fat yogurt. I forgot to mention that. That's part of my breakfast as well, which has 80 calories per serving and some fruit, but very little sugar because a lot of the yogurts, for example, do have added sugar, and there's many foods that are out there, both packaged and unpackaged, that contain sugar in amounts that can be quite detrimental to metabolic health. And so added sugar is definitely at the bottom of the list. And there's all kinds of complexity in between, but those are kind of the spectrum of carbohydrates, I think, generally think about.
What about, so there's obviously there's a lot of added sugar out there in our food environment, but what about like natural? So when we think about fruit, for example,
Right.
Fruit often has a lot of sugar naturally. Are some fruits higher in sugar? How's that sugar, that sucrose different from other forms?
Well, the answer is yes. Fruits differ in their sugar content. I'm not a food scientist, so I don't have those numbers at the tip of my tongue, but it's very easy to assess that just by the taste. The sweeter the fruit, the more the sugar. It comes from fructose. Glucose, which is a simple carbohydrate, does not have the sweet taste that fructose has. So we're dealing with fructose, which is a special form of simple sugar that is found both in fruits. It's found in foods that have added sugars because it's part of sucrose, which is the thing we usually use to sweeten things. That's a molecule that has both glucose and fructose. But it's the fructose that has the main metabolic effects, at least in the things that are most closely connected with excess adiposity. Metabolic conditions that can increase heart disease risk can be aggravated by fructose. So within fruit, however, not only is there variation in the fructose content, but unprocessed fruit, that is when you haven't ground it up and made juice out of it, will contain that fructose, and the sugar is in a form that's attached to usually forms of fiber. So it's the context in which the fructose is consumed that can attenuate the metabolic impact of the sugar by slowing down its absorption, maybe even reducing its absorption to some extent. Because when one takes a slug of pure sugar, in its isolated form, or an added sugar such as sodas, you can get a big spike in glucose, which stresses the insulin machinery and can ultimately promote changes in the ability to handle that sugar as the insulin capacity begins to be stretched too far. So within fruit, one, as I mentioned, does not get that slug usually if you're not using a highly processed food, if you're using a real. So, I mean, again, I just take this on the basis of taste. Oranges, which is my one concession to sugar, is a little bit of juice does have sugar, and that's something one doesn't want to overdo. But within its natural form, within the orange itself, that not only is there less sugar, because one generally does not eat as much sugar coming from the natural fruit as one does from the juice. So it's a better way to consume fruit. And then when it goes down the list, as fruits get less sweet, it's because they have less sugar. And within even a category, I mean, again, this is just a personal experience. You can buy different forms of apples. I mean, there's a huge amount heterogeneity in the food supply. You can get some apples that are sweeter than others. And it's very hard to get this information from any kind of inventory. The USDA keeps a list of composition of foods, which one can get lost in huge database. But even with that information, you don't know for sure when you're buying your fruit, which I do myself. I go shopping for my own food, and I can only tell, in the case of sugar, for example, what is sweeter than others. And as I said, even a range of different apples, and over time, even that can vary. So nutrition is a very difficult thing to actually get into that level of quantitative data because so much depends on where the food is coming from, how it's processed, even the time of year. So it's one of the reasons that nutrition science is so challenging.
Mm-hmm. Yeah, obviously, I mean, this is an inherently complicated subject because there's just so many facts, known and unknown, out there that have to do with nutrition and how our bodies respond to it. One of the things I want to do in this discussion is give people a sense for how ideas and guidelines get set and how they've evolved over time. And I thought we could start with going back to the mid 1900s. And there was this thing called the diet-heart hypothesis that was formulated and became highly influential. Can you just briefly summarize what that was and sort of how it came about for people?
Okay, well, that's something I've been deeply involved with, both personally and historically, although I didn't get involved in the field until a couple of decades later. I inherited a lot of that early information and evolved my own work from it, as well as my recommendations that I've promoted for dietary guidelines. But it starts really even earlier than the 1950s, when it was shown in the early 1900s that cholesterol can form plaques in the arteries and lead to heart disease. And so blood cholesterol was recognized as a risk factor for heart disease early on. But what happened in the 40s and 50s, and I think the diet-heart hypothesis you're referring to relates to the work of people like Ansel Keys, who did studies showing quite properly, actually, that high intake of saturated fats in the diet increases blood cholesterol levels, and particularly the low-density lipoprotein, or LDL, bad cholesterol, and connected the dots, both in terms of the relationship of dietary saturated fat intake to cholesterol levels, and also ultimately to heart disease risk. That was not just his work. In fact, it was over time a series of observations that made those connections, which have been challenged, including from work that I've done, as being perhaps misleading in terms of the causal relationship of saturated fat to heart disease. But that was really the basis for the designation of the diet-heart hypothesis, really focused on saturated fat. But early on, there was even what in retrospect was a real error in considering total fat as the equivalent of saturated fat, so that the guidelines early on were focused on limiting total fat intake with the secondary objective, the hidden objective in a way, of limiting saturated fat and lowering cholesterol. But it was in the context of overall low-fat diets, which also then carried with it a shift from fat content. This gets into the macronutrient composition. If you're dropping one thing, you're going to increase something else unless you're reducing total calories. And the increase was in carbohydrates, which was really the wrong direction to go. But to your question, that relationship between saturated fat, cholesterol, and heart disease has formed the basis for dietary guidelines over the years. The McGovern Commission, which started off the whole USDA HHS dietary guidelines process, which happens every 5 years, originated with the McGovern report that highlighted the importance of saturated fat in heart disease risk as a major feature of that. And again, it was in the context of limiting total fat, not limiting carbohydrate. And that really has sort of stayed with the guidelines in one form or another. I'll just mention historically that I sort of came into the picture much later, inheriting those guidelines, and both in my own research, which we can talk about, as well as work of many others, came to realize that there were some real holes in that mechanism that may have led to misunderstanding of how to manipulate diet, in the case of heart disease risk, at least, in the context of a population which was progressing from early days, even before the 50s, when people tended to be more active and were perhaps more sensitive to dietary cholesterol and saturated fat. But over the years, and we can talk about this as well, we sort of converted to a society where the majority of individuals are overweight and have metabolic issues connected to adiposity. And the guidelines that were focused on just lowering cholesterol by reducing saturated fat no longer covered the metabolic problems that individuals face when they develop this so-called metabolic syndrome. So the population has changed, but the guidelines have been really slow to evolve to really meet the differing metabolic responses of individuals in the current population, and they continue to emphasize the same.
So if I'm hearing you correctly, it sounds like, roughly in the mid 1900s, if we go back a few decades, the thinking was, saturated fat appears to raise blood cholesterol levels. High blood cholesterol is correlated with bad cardiovascular outcomes.
It is.
And from that, the conclusion was basically drawn in terms of how the guidelines were set, that one should minimize not just saturated fat, but total fat, and replace that with carbohydrates. And so at the time, sort of when that was the thinking and that became influential, what was actually like the strength of the evidence? Were these coming from randomized controlled trials? Were these mostly just correlational observations that were made? How good was the evidence at the time for this idea?
Right. So that's a good question, and I'll try to keep the answer simple. But there's some aspects of this that really require some detailed explanation. As you mentioned, there's really two sources of data that can be used to try to establish causality. One is randomized controlled trials, where one takes a population and assigns them to one or another diet and looks to see what the consequences are in terms of health outcomes. The second is observational data, taking usually recorded data, historical data, self-reported data, and dietary intake, and connecting that with various other measurements, but ultimately with outcomes. Both of those approaches, and particularly the observational data, can be flawed in terms of how one interprets causality, because it's not as simple as either a genetic test where you've got one gene doing one thing and that causes a certain outcome. That's as close as we get to causality, I think, in research. In terms of treatments, again, it's easier to establish causality if one uses a single molecule drug, such as a statin drug, which lowers cholesterol. We know the cause of that cholesterol lowering is statins. When it comes to diet, we have all these variables which we just talked about, plus the fact that when you're changing a macronutrient, such as fat, against carbohydrate, if you're changing that distribution, you can't really be sure what any outcome related to heart disease is due to that change per se, because there's too many other variables that are changing. You can't control all of them. And observational data are even more deeply flawed, because when it's dealing with historical records or patients, or they're recording their intakes and they're being analyzed, but as much as one can do to try to validate that type of questionnaire approach in particular, it still has some serious questions as to whether this is really a valid measure, particularly of diet over time. Group at Harvard School of Public Health has done the best job, or one of the better jobs around, in terms of trying to standardize that approach, but it's inherently flawed, and it's really dependent on statistical considerations that also can carry some downside in terms of how one interprets the causality aspect. So causality is difficult to establish in both of those systems. But if you want me to go back to your question, the randomized trials that were carried out in the 60s. I can't remember the exact dates now, but there were several large randomized controlled trials in which the goal was to examine the role of dietary fat in heart disease risk. And we've summarized that those trials in various ways did show that diets that were limited in saturated fat and were higher in another form of fat, unsaturated fat, particularly polyunsaturated fat, which is in the chemical sense quite different from saturated fat. Those diets where saturated fat was reduced and polyunsaturated fat was increased did lower heart disease risk. There have been criticisms of each of those studies that I won't go into in terms of various features that kind of dampen the conviction of causality. But the main issue that I've pointed out, which has been overlooked in general, is that those diets were very high in polyunsaturated fat, which is the kind of fat that comes from seeds and nuts, for example, or in salad oils. There's a whole contingent of people that feel that polyunsaturated fat can induce other adverse effects. But in these studies, the intake was very high, and one can't be sure whether it's the reduction in saturated fat or the increase in polyunsaturated fat that was responsible for the benefit. And that has evolved in the observational studies to considering the ratio of saturated fat to polyunsaturated fat in the diet as an index of metabolic impact on heart disease risk. Mm-hmm. But one doesn't know really whether it's the numerator or the denominator. Is the polyunsaturated fat good guy and saturated fat neutral, or saturated fat bad? Saturated good. You can't dissect them.
I see. So they did studies where they looked at saturated and polyunsaturated fat intake. Saturated fat, when saturated fat went down and polyunsaturated went up, they saw some benefits in terms of health outcomes, but they can't be sure if it's one or both of those. Is it the saturated fat going down or the poly going up?
It was interpreted as the saturated fat going down. I mean, all the guidelines since then, and some definitive so-called reports from American Heart Association that justify current guidelines, for example, point to those randomized trials as a key element in making the connection between saturated fat and heart disease risk, but really did not consider the fact, in my view, that there could be benefits through very high intakes of polyunsaturated fat that were responsible for the benefit, and saturated fat was really just a sort of a neutral background component. That would be the extreme other interpretation of those studies, which has not been generally talked about.
Yeah, and one other thing that strikes me as being potentially relevant too, especially when we look back at studies that were done years and years ago and try and interpret them for people today, is let's just say, okay, you look at those studies and someone decides, I want to, say, increase my polyunsaturated fat intake or decrease my saturated fat intake. At the time these studies were done, when someone eats polyunsaturated fats, are the foods that were giving them those fats different back then than they would be today?
Well, right.
Yeah.
No.
And so I want to talk more about how these dietary guidelines are actually established. So like literally, how does this process work? How do they determine which studies to consider when they set when they set the USDA dietary guidelines? How do they evaluate the studies, and what does that look like?
Well, that's a question that has a lot of issues that have been raised recently, in particular about the process. Originally, as I mentioned, they evolved from the McGovern report and related data from a group of individuals who were selected based on their expertise in this area to come up with formulas for dietary guidelines that were, as much as possible at that time, based on ways of estimating the distribution, what the optimal distribution of various fats and carbohydrate intake, for example, should be advised for the general population. So that was based on a committee process that evolved subsequently to, and I don't remember exactly the time course of when the transition occurred, but over the subsequent years, at some point, this was formalized into a 5-year cycle of dietary guidelines that were generated and are being generated by committees, or at least there's recommendations for these guidelines that are established by committees selected for their expertise in various aspects of nutrition and health. And they meet every 5 years and prepare reports. Those reports have been based on what was thought to be the available evidence to support the recommendations that committee came up with. And that process has undergone some serious evaluation and criticism based on the way that the evidence is presented to the committee and the kind of evidence that's available to present to the committee. So again, I'm not sure, I can't give you the exact timeline, but I think maybe it was probably about 10 years ago. I was part of a committee that was appointed by the National Academy of Sciences, the Food and Nutrition Board, and the Institute of Medicine to provide the evidence at that time to support, or at least to allow the dietary guidelines processes to evaluate the effects of various macronutrients on health. And that was really the first time there was ever a targeted effort to, in an unbiased, global way, as much as possible, assemble data. So we met for quite a long time. It was quite an intensive effort because we had to cover fats and the different kinds of fats, carbohydrates, protein, cholesterol, and it was a very extensive process. And that presented data which eventually led to some, it moved the needle a little bit on the dietary recommended intakes of fat and carbohydrate, which we can talk about perhaps if you'd like. But that has only been done once. That was a one-time effort. And since then, the guidelines, it may have been more than 10 years ago, at least the last several 5-year cycles, while they've certainly alluded to that inventory that we assembled, have tried to update as much as possible, as much as they thought possible, the evidence base for making their recommendations. That's been criticized because it hasn't always been up to date. In fact, the very last cycle, I've been part of a group that have published critiques of that process. And as a result of those critiques, there was another panel convened by the National Academy, which I couldn't serve on because I was conflicted in terms of some of my other research. But I was an advisor to that process, which was aimed not at the guidelines themselves, but at the process by which the guidelines are developed. And a series of recommendations were made, including the way the evidence is developed, keeping it up to date, making it transparent, dealing with conflicts of interest that may be represented by the members of the committee that should be considered in the end as part of the assessment of their product. So this, and we just published a paper recently. I think it's been published. I can't remember. I think it's been published, where we pointed out that those guidelines have really not been fully adhered to, even in the last cycle. So we have a current cycle that's due in 2025. I don't know where that stands. I certainly have not been in touch or involved with that current cycle in any way. But at least there has been recognition that through this report and through other critiques, that the evidence base has to be strengthened beyond what's been currently used. The other important aspect of the dietary guidelines process is that everything I've just talked about relates to the work of a committee of scientists, health scientists, and people that have expertise in various aspects of nutrition. There's also been concern about the effect on the environment, which goes a little bit beyond the health effects of the foods themselves. So it's a mixed set of disciplines that form this committee, but their report does not represent the guidelines themselves. That report is provided to the U.S. Department of Agriculture and the Health and Human Services departments, which jointly oversee the production of the dietary guidelines that are actually implemented for policy purposes and for public education. And they don't always accept the specific recommendations of the science committee. And there's been concern about that because of what I think can be obvious concerns that the USDA in particular has a mission not only related to food and the health of the population, but also the agriculture industry itself. And that can, despite efforts to avoid those conflicts, nevertheless, there's a concern that some of the ways that the scientific report has been implemented at that level have been influenced by considerations that go beyond the science.
I see. So these committees of scientific experts, that's simply one input that goes in to how the USDA and these organizations set these guidelines. There are other inputs coming in from other places. I don't know if it makes sense to talk about what some of those other inputs are, but even within the scientific committee, you mentioned, the possibility for conflicts of interest. What are some of those conflicts that you've seen over the years?
Well, I don't want to point figures, in part because I've had my own conflicts in terms of where research support comes from, which have led me to be involved in some activities, but not others, where those conflicts could come into play. And the reason for this is one that I'm very sympathetic to, and which I think can be strongly justified, and that is nutrition research, particularly regarding effects on chronic disease, long-term health outcomes of dietary changes is extremely difficult to do. It requires teams of investigators. Proper studies should have many participants. They should be long-term, and we start adding ideally providing the foods themselves as a way of assessing the impact of the diet on health outcomes. All of that is an extremely challenging set of issues that make these projects quite expensive and difficult to support. We have government support coming from the National Institutes of Health, primarily some from the USDA, that have supported research, that supported some of my own research. And there certainly is interest within those agencies for providing strong science. But the scale of research and the cost of research and the number of issues that have to be dealt with really exceed the capacity of those institutes to support research. So we as a group, and although I'm sort of moved away from this in my own research, but over the years, I was part of this group that was really relied very heavily on support from industry to have the funds and the resources to be able to do studies on that scale. And the key is, as much as possible, to separate the work of the project from the interests of the sponsors in those cases. And that can be difficult and sometimes almost impossible to prove to the critical public. Is saying, well, are these results really true results, or have they somehow been influenced by the sponsor? So the problem is that many of these experts on the committee, getting to your question, have done research, which is perfectly good research published in high impact journals, which would not necessarily be questioned. But in those cases, there was a significant support coming from food industry sources that could be the basis for challenging the possible conflict.
Yeah, so it sounds like just like the nature of this research is that the studies to be done properly at a large enough scale with a high enough sample size and to be done well, there's so much that goes into it. It's so resource intensive that it's so expensive that there's not enough funding coming from places like the NIH, et cetera. And so a lot of it then is also receiving funding from industry. And because something gets funded from industry, that doesn't necessarily automatically mean it's contaminated in any way, but there's always that concern.
Right. The best. That's exactly right. You just described what I was really getting at. That is a fact of life in nutrition research, at least as it relates to long-term health consequences of the major macronutrients. We really require, in most cases, some ancillary support. And that can come from industry. And the way that's dealt with, or should be dealt with, is when publications appear. There really should be a statement saying that these results were not influenced in any way by the sponsor. And that can be true. For example, let me give you my case as an example. When I started off looking at dietary effects on heart disease risk and lipids in particular, I was facing some of the same issues you discussed. I did get a grant from NIH at the time, but it was a very small grant. I think we studied like 6 people. It was an intensive study in this tiny group of individuals, and I realized at that time that wasn't going to cut it. So I took advantage of an opportunity offered by the National Dairy Council to fund a large program, which was initially $1 million a year for 5 years, a big center, which I was really excited about, the opportunity that presented for doing things on the scale we talked about, doing mechanistic studies as well as human intervention trials. It was highly competitive. They awarded one grant, and it was ours. So we actually got that center funded through this amazing resource. And it raised all the issues we just talked about. How are we going to conduct the science in a way that was not connected to the sponsorship? And so that's the sort of thing that we dealt with and should be dealt with, is established at the outset. If you're taking research funding from groups such as National Dairy Council, you want to be sure that what you're coming up with at the end is not somehow incorrectly assign benefit to things that should not be beneficial.
When a group like that sets up, when they decide to fund research like that, how exactly do they advertise it? Are they just saying we want to give someone money to do research in general on dairy, or how specific are they getting in terms of what the funds should be used for?
That's an interesting question. It takes me back. I mean, this grant, in fact, this goes back to, believe it or not, 1989. Which is when this program in my lab got started, it was advertised to people in nutrition research, in parts of nutrition at the university. So the announcement was widely distributed. So there were quite a few applicants for this from across multiple institutions, and so that process, I think, was fairly undirected. It wasn't an effort to fund specific people. I can tell you, I didn't expect to be funded. I was thrilled when it turned out we were funded, but there was nothing in advance that would have steered it that way or any other way on that side of things. Then it underwent, and this was the brainchild of the scientific leadership at the National Dairy Council, which does have a science arm, and still does. And what they asked for was important findings related to diet and health, and we're obviously very interested in the role of dairy in that regard. That was certainly one of the driving forces to establish the science that would, I think, in their view, strengthen the case for some features of diet and health that could be favorably affected by dairy. So that clearly would be in the background for the formulation of this program. But when it was actually delivered as a request called the Request for Applications, or RFA, it was sent out as an RFA. with broad categories of work that would be funded, genetic work, work in clinical trials. So, and this is the way NIH functions as well. It was very much based on an NIH, the federal model, where the various components of the program were suggested in the announcement, and then we were asked to respond to those components in ways that would be considered appropriate for the grant program. That underwent pretty rigorous peer review, which is, of course, also should be part of any process for research, whether it's industry sponsored or not. But because of the scale of the funding in particular, and the unique nature of this program at the time, and of course, I don't remember who the reviewers are, but they were, our proposal, which was sent in response to this RFA, was reviewed at two levels, both by external scientific reviewers and also within the National Dairy Council, and also the USDA, which oversees the Dairy Council. And I should mention that the funding that was used to support this program comes from something called the checkoff program, which, whereby a certain amount of money that comes in, I forget what the exact rate is. It's a few cents or whatever per dollar of dairy products that are sold are allocated, have been allocated to marketing of dairy, but that category was divided into research as well. So there's both research and marketing, and that amount of money was available through this checkoff program for the research side. And the research was separated from marketing. We were not involved in the marketing. We were involved in the research side. And as I said, that was rigorously reviewed. And we subsequently, in all our papers since then, because we were able to renew this program for a couple of decades, actually, I stayed with this support, which continued to generate observations that were both publishable, relevant to human health, but also of interest to the sponsors. And those are all reviewed and published in peer-reviewed journals. And I think in many, I can't remember exactly how we handled this initially, but the important thing is that we were, in our contract with the sponsors, ensured that we could write whatever we needed to write based on our science without any input from the sponsors at all. They were given the opportunity to look at the papers before they were published, particularly if there were any intellectual property or patent issues involved, which there haven't been in my case. But that was strictly for review, and they could comment, but they had no ability to in any way impact what we actually were saying. And that is the important safeguard that one really has to enforce. And I think the kind of people that we have been considered and have been involved with the dietary guidelines process, I'm sure are all understand that and practice that approach. But it nevertheless, on paper, leaves this connection, which you can't erase. That connection just is something that can always be used to challenge results.
So when we think about what the USDA dietary guidelines say today with respect to dietary saturated fat, dietary cholesterol, and cardiovascular disease, what do the guidelines say today? And what is your view on how well those guidelines reflect the totality of the relevant literature here?
Okay. So this is another big question. And you'll pardon me if I have to spend a bit of time giving you all the reasons that I can bring to bear on answering it, all the issues that I've been involved with myself, as well as those we've culled from work of others in the field. So the guidelines relatively early on considered the need to limit saturated fat as a key element, particularly specifically for heart disease prevention by lowering blood cholesterol. That's the argument that has stood the test of time in terms of how the guidelines are currently developed and implemented. A cut point of 10% of calories of saturated fat was established early on. That is, the guidelines did and continue to recommend that individuals limit their intake of saturated fat to less than 10% to reduce the risk of heart disease. And that was embedded in the guideline for total fat, which was in the federal guidelines set at around 30%. That's been somewhat liberalized recently. I should mention that there were guidelines, I could have mentioned this earlier, that were also developed for heart disease health by the American Heart Association. And just as a brief aside, I became chairman of the American Heart Association Nutrition Committee a couple of decades ago, and inherited these prior guidelines for total unsaturated fat, as well as other elements of the diet for heart disease health. And I chaired the committee that wrote a set of guidelines in, I think, 1996, ultimately, that really extended the previous approaches adopted both by the government in their guidelines, as well as the American Heart, for total unsaturated fat. But at that time, I was doing work of my own, which we can talk about perhaps as part of this discussion a little bit later, that convinced me that cut point was really not based on anything specific to that 10% figure. And that was really also consistent with what we found in the report that I had mentioned earlier, convened by the Food and Nutrition Board. And we recognized that 10% figure was really a way of just hitting a level that would reduce the average intake of saturated fat in the population, at least in those years, and thereby lower blood cholesterol levels and heart disease risk. So it was set as a target, not because the 10% was some magic number, but because that seemed to be a feasible goal that could be achieved in the population as a way of pushing the risk for the population down for heart disease. So that has stood up. So the question is that appropriate at all? And I can give you a whole set of concerns that we've raised and published on that, in my view at least, challenge the idea of having a specific cut point like that at all. And it starts with the fact that saturated fat is really a way of describing a particular class of fatty acids, which constitute fat. There's, a fat molecule has 3 fatty acids attached to it, a glycerol backbone that forms a triglyceride. And it can also be phospholipids and other fats, but the term saturated is applied when the bulk of those fatty acids have all of their bonds saturated with hydrogen. We can discuss the chemistry if anybody's interested, but that's where the word saturated comes from, is that these are a particular form of fat that have this property, as opposed to fats that have the same number of fatty acids, but that don't have as much of the saturated fat component, have more fatty acids in which the hydrogen is not saturating those bonds. So they become unsaturated, either monounsaturated when there's one bond that is that loses the hydrogen, or polyunsaturated where there's several, and there's different classes of both monounsaturated and polyunsaturated, and there are different classes of saturated fat. So we have across the board a huge heterogeneity in the chemical nature of both the fats themselves, saturated, unsaturated, polyunsaturated, but within each of those categories, there's heterogeneity, and that certainly applies for saturated fat and fatty acids in particular. So having said that, one can ask, well, why have a saturated fat cut point? Why not talk about specific fatty acids? Well, that gets really complicated because we don't have the data. We certainly don't have the outcome data. That gets back to the point where we're not going to do a study where we change one specific fatty acids usually and follow somebody for 30 years, make sure they're following the diet and see what happens. You just can't do that.
It's just not feasible. Yeah.
So that's the reason for the lumping. So the lumping is based on this evidence, which is uncontrovertible, that if one substitutes saturated fat for either unsaturated fat or carbohydrate, one does raise the LDL cholesterol. That's in most cases, not everybody. There's variation in that response. For example, people that are obese, and we published a paper, and others have shown, if you're overweight, kind of paradoxically, you don't get that effect at all.
But in general, if you increase saturated fat intake, you increase LDL cholesterol.
Over the population in general. As I say, there's variation in that. It doesn't apply to everyone, but yes. And we and others have shown that repeatedly. So there's across the population, that relationship is well established. Similarly, there is evidence which supports this guideline that raising LDL and also the other direction, lowering LDL, affects the risk of heart disease unfavorably or favorably. If you lower LDL, you see a proportional reduction in risk, but that may depend on the way that the diet is changed, or the way the saturated fat, or the way, it may depend on the way the cholesterol is lowered, and saturated fat may have some effects that differ from other mechanisms for lowering cholesterol, limiting saturated fat, such as statin drugs. So you can't necessarily extrapolate from the data in which lowering LDL has been connected with heart disease to make that connection with saturated fat. And again, there's multiple reasons for that, one of which is the heterogeneity of the saturated fat. The other is the foods that the saturated fat is contained in. So one of the enduring underlying aspects of our criticism of this guideline is the focus on saturated fat as a class, as opposed to specific foods containing those saturated fats, which differ, and the potential for differing saturated fats to have different effects, the substitution of other nutrients, how that reduction is achieved. So about, I guess, probably 13 years ago now, we decided to do a review and ultimately performed what's called a meta-analysis, which is a formal statistical analysis of studies that have been thought to support a relationship of saturated fat to heart disease risk through this cholesterol mechanism. And as we talked about a few minutes ago, that included the randomized clinical trial data, and even a few trials since the early ones, but much more data coming from the observational epidemiological data, where one has large populations and tries to connect the dots in terms of saturated fat and heart disease. And what we found is that the literature at that time failed to show a significant relationship between saturated fat intake itself, per se, and heart disease risk. If you try to just, as much as possible, particularly from the epidemiological studies, is to just narrow in on saturated fat intake as a component of diet as assessed by these imperfect tools. If you use that data, one could really not show a significant relationship to heart disease risk, and that created a furor at the time. It was I was sort of somewhat prepared for it, but not the intensity of the pushback, because here we were taking down one of the principles of the dietary recommendation for heart disease risk reduction. And in my case, since much of my research is focused on LDL, it was a little bit ironic because I certainly never backed away from the importance of LDL and heart disease risk, but we could not connect those dots, and there may be many reasons for that, starting with the foods themselves and all the things we talked about in terms of the context in which the saturated fat is consumed. But here is where I'm going to take a little tour through an aspect of this that relates to the LDL side of things.
Okay.
Because, when I began my own research on lipoproteins, or at least when I continued to do work that I started when I was actually in medical school, but went on to study lipoproteins in a lab at University of California, Berkeley, which was really the lab where lipoprotein science was first started, really in a way that allowed the study of different kinds of lipoproteins that could be isolated and prepared and analyzed in depth. My research really focused on LDL and the fact that LDL is not just cholesterol. Cholesterol is a component of what we call an LDL particle. And the particle is a spherical molecule that is circulating in the blood that transports cholesterol. So when you measure LDL cholesterol, you're measuring the cholesterol in that particle. But there's many other features of that particle that come into play when it comes to biological effects of the LDL particles. And just jumping ahead, over the years, there's been progressive acceptance, I think widespread acceptance of the fact that it's the LDL particle that we should be considering as the vehicle that brings cholesterol into the arteries for plaque formation, not just the cholesterol content of the particle, but the particle itself. And getting back to my early work in the lab, using the tools that were available in that really superb research environment, with a lot of expertise in separating lipoproteins, we discovered, and since rediscovered, that LDL is not a single class of particles. That LDL particles represent a spectrum of particles that can be differentiated based on their size. Particles can be smaller or larger, and as they get larger, they have more lipids, including more cholesterol. So one has a spectrum of particles ranging from larger cholesterol-rich LDL to smaller cholesterol-depleted particles. And what we discovered, and which has subsequently been confirmed repeatedly, is that counterintuitively and somewhat paradoxically, the strongest relationship of LDL particles to heart disease risk was not with those particles that contain more cholesterol, but in the smaller particles called small dense LDL that are a distinct class of particles, which have been shown to have properties beyond their cholesterol content, which can form the basis for a more toxic effect on the arteries.
Ronald, I'm hearing some tapping in the background.
Oh, that may be me.
Okay. Yeah. Okay. So it's not purely the cholesterol per se here. It has something to do with the particle size.
With the type of particle itself. And the particle size is a way of identifying these particular particles, the smaller ones that have these more damaging effects on the artery, including, for example, the fact that they are more likely to stay in the bloodstream than larger particles because they are taken up less effectively by the liver. So in order to get cholesterol out of the body, and this is the basis for all of our efforts to lower blood cholesterol, most of those are focused on promoting means of increasing LDL removal from the blood. That's the way statins work, for example, by interacting with receptors at the cell surface in the liver. Those smaller particles have less ability to bind those receptors, and it's been shown that as a result, they circulate in the blood longer, and as a result of that, there's greater exposure to tissues, particularly the artery itself, where the blood is circulating, that can trap these particles. So this prolonged residence time is a big issue that may point the finger at a mechanism, at least part of the mechanism, for the relationship of these particles to heart disease risk. But it's also been shown that they can enter the artery relatively easily, partly based on their smaller size. And they also have physical properties that cause them to bind more tightly to the artery. Sometimes we think of just things going into the arteries as the only direction, but we know that things can go in and out of arteries. But these particles can go in and have much more trouble getting out, so they get trapped. And once they're trapped, it's been shown, we showed and others have shown, that they are more readily oxidized. They undergo oxidative properties once they are taken out of the plasma. We don't have an antioxidant environment to protect them from oxidation. That oxidation promotes a number of changes which lead to inflammation and the buildup of plaque by mechanisms that extend the damage due to the cholesterol itself, so that inflammation becomes a big part of the evolution of a plaque from a more benign to a more malignant form that can cause heart attack and stroke when it's in the brain. That inflammatory aspect initiated by oxidation is another feature of these small LDL that to which the risk has been attributed. And all of that is in relation to larger particles, which can have these effects, but to a much differing degree. So that going back to the question of diet and LDL, led me to include in my proposal for this program that I described earlier that we initiated a number of years ago. One of the major projects was to test the current idea at the time that a low-fat diet would be beneficial for heart disease risk, and we hypothesized that that would benefit those small LDL particles because that's what we thought would be a mechanism for a benefit of reduced dietary fat. Well, what we found is what changed the direction of my own research and led to some other impacts in the field, is that following that traditional diet, low in fat and high in carbohydrate, actually had rather small benefit on the people with heart disease risk who had more of the small LDL. We classified them as what we call pattern B, small LDL, versus pattern A, which is large LDL. These are two distinct subgroups of the population. The pattern B individuals, the ones at higher risk, showed some benefit, but at the same time, 25% or so of those who had a normal lipid profile, which we call pattern A, actually converted to pattern B. So low-fat, high carbohydrate appeared to worsen the risk in a subset of individuals who converted to this higher risk pattern as a result of this diet. And we subsequently showed that this is not related to the fat content changing, it's related to the carbohydrate content changing.
So for about 1 in 4 people, increasing your carbohydrate consumption has this effect.
In that particular population, yes. Yes. And we also, I just want to say that this was a healthy, non-obese population. We and others have shown subsequently that if one is overweight or obese, that there's a much higher prevalence of this high-risk trait. And we now know that body weight, particularly what we call visceral adiposity, fat in the belly or fat in the liver for that matter, in excess can drive this trait as well. And so in the end, it's two separate mechanisms, one involving carbohydrate, the other involving body fat, that can contribute to the formation of this small LDL profile.
So what exactly are drugs like statins doing, and how effective are they at doing, what do they change in terms of blood markers, and how good are they at, in terms of cardiovascular disease risk?
Okay, so statins, were just a huge breakthrough in the field as a means of lowering heart disease risk, and their efficacy has been shown repeatedly in terms of heart disease risk reduction. What are they doing that leads to risk reduction? That's the question. So it starts with cholesterol. Statins specifically block the activity of an enzyme called HMG-CoA reductase, a very specific inhibition of that enzyme, which is a crucial enzyme for cholesterol synthesis by the liver. As a result of that effect, the liver goes through a series of responses that result in increased levels of these LDL receptors that suck more LDL out of the blood and bring it to the liver. So the net result of this mechanism is a lowering of LDL, mainly through reduction, through increase in clearance from the blood, and to some extent by reducing the synthesis of these like proteins as well. So the LDL lowering effects are well established. What we've shown, and others have shown, is that this effect is more pronounced for the larger LDL particles, and that the small, particularly the very small LDL, are more resistant, and that's because of the feature I mentioned earlier, that the particles have a lower affinity for the LDL receptor.
And so
there's a net. Just I want to say there's a net reduction in everything else. So there's a up to a 50% reduction with the more potent statins at the higher doses, 50% or more reduction in LDL particles, which includes most of the small LDL, but not all of them. That's a benefit. And the second mechanism, which is also, I think, very important, goes beyond cholesterol lowering, because by inhibiting this enzyme, one can also reduce products that are pro-inflammatory. And as I mentioned, inflammation is a key element of plaque development and conversion to a more dangerous form that can cause heart attacks and stroke. And statins have an anti-inflammatory effect. And a marker for that is called C-reactive protein, or CRP, which a friend and colleague of mine, Paul Ricker, has been instrumental in establishing as both a marker and potential target for statins, because statins lower CRP as an index of their anti-inflammatory effect. And the combination of those two mechanisms, I think, are really important for the ultimate benefits that statins have been shown to have.
Mm-hmm. What's the relationship between dietary cholesterol intake and blood cholesterol levels?
Okay, so that's another question. This one I'll try to just zone in on the fact that when I was assigned to this committee that I mentioned for the Food and Nutrition Board, National Academy of Sciences, I was given the task of writing the chapter of this volume on dietary cholesterol. That was my topic. And I knew something about it. And as I said, I was at that time involved in the American Heart and Nutrition Committee, and we were continuing to advocate at that time a generally accepted historical recommendation for limiting cholesterol intake to 300 milligrams a day, which is the equivalent of about one and a half egg yolks per day, something in that category. That, of course, comes from other sources as well. Animal fats contain cholesterol. So all of that was a guideline that was out there. And I was charged with, as part of this process, assembling the evidence to support that guideline. And what we came up with was that there is an effect of dietary cholesterol and blood cholesterol levels, and it's LDL cholesterol in particular. But the magnitude of that effect was really pretty tiny. Certainly compared with, for example, the saturated fat effect we just talked about. Dietary cholesterol has a small effect, which if one extrapolates that to its predicted effect in heart disease risk, it would take a population of the world, it would take a huge population to prove that that was a deleterious effect. It was so small, and certainly did not support any particular number, because there was it's a continuous relationship. Of course, the risk and the cholesterol levels both went down as cholesterol intake went down, but the net change in those measures, in those outcomes, was really not enough, in my view. And we try to get this in the report to justify that guideline, which could be used as a benchmark, but not based on specific science. So speed forward for I don't know, another 10, 15 years, and the U.S. dietary guidelines, as well as the American Heart Association, finally recognized that this was not something that they should really be pushing based on the science. And so that cholesterol guideline has been taken out of the guidelines, which finally, I think, represents the right move scientifically. I should mention that most of the cholesterol that enters our system is actually produced by the body. The amount we consume, if it's 200 to 300 milligrams a day, for example, within that guideline, should be compared with the 700 or 800 or 900 milligrams per day coming from the synthesis of cholesterol by the body, by the liver and other tissues. And so when one lowers dietary cholesterol, one is not taking out a major source of cholesterol entering the system, plus which there's a lot of variation in how cholesterol is absorbed. There's receptors involved that can cause a relatively big response to dietary cholesterol, and others that small response. So we have, on top of the mechanism, we have a huge variation in the sensitivity of any given individual to dietary cholesterol. And it's very difficult to set a number that it would apply to the whole population.
So if a lot of the cholesterol is produced internally, why does one have high cholesterol? What are the causes of someone getting very high cholesterol levels?
Okay, so let's start with the very high cholesterol levels, because that's the easiest to talk about. Some of the groundbreaking work that ultimately led to a Nobel Prize by Drs. Goldstein and Brown, who were studying this, was based on individuals who have what's called familial hypercholesterolemia. They have a genetic form of elevation of LDL that is characterized by a number of features, including, importantly, affected family members, parents who carry this, one or more parents who carry this diagnosis. And it was well established through many studies that if one has a more severe form of this condition, which we call FH, familial hypercholesterolemia, one is at high risk of heart disease. If one has the most extreme form, when one inherits the gene from both parents, LDL cholesterol levels can go through the roof. They can be 4 or 5 or 6 times normal. And younger individuals, even children who have this condition, can have severe coronary plaque development and heart disease. And if one has one copy of the gene, which is present in about 1 in 200 or 250 individuals in the population, not rare. It's not super common, but it's certainly not rare. One is susceptible to the same trait, and one can have LDL levels that are high. And the basis for that is mutations in the gene for the LDL receptor that prevent uptake by the liver of LDL particles. It prevents the LDL from binding. And so that cause is absolutely well established. Not everybody with this genetic trait will get a heart attack. There's variation in other factors that might affect risk. But in general, there's a very strong connection between the presence of this gene and its consequences on LDL and the risk for heart disease. So it starts there with these very high levels. To give you an idea of the numbers, we generally consider LDL cholesterol levels of less than 100 to be in a healthy range for most people, lower for those at higher risk. People that have the severe form of hypercholesteremia I just mentioned can have levels of 500 or 600. People that have the intermediate form with just one dose of the gene can have levels of 2 to 300. And so we've established a level of 190 as a cut point, again, somewhat arbitrary, but it's the point at which if you have levels above that, you're very, very likely to have inherited either that gene or other similar genes that block the removal of LDL from the blood. So that mechanism is well established. Beyond that, genetics has given us a lot of data about other genes as well. That gene, as well as others, have been studied extensively in relationship both to LDL levels and heart disease risk. And so we have ways of collecting genetic information that can allow us to get a risk score. That is, how many traits are one carrying, and this is across the whole genome, across all genes. You can scan for genes that have individually less extreme effects on LDL, but collectively can have a significant effect, higher score, higher risk. That risk score has been related to heart disease risk as well. So there's genetic evidence both at the extremely high level, but also at the more conventional LDL levels below 190, that genetic factors, for the most part, affecting the ability to clear LDL out of the blood, can show causality of LDL and heart disease risk. So genetics is a big part of it. Diet plays on top of that. So in terms of the spectrum of things that can affect LDL, genetics is kind of the backbone framework, which we all inherit, either tendency to high LDL or not, depending on what our parents have given us genetically. On top of that, we have diet. We just talked about the effects of dietary saturated fat and cholesterol. I mentioned that the dietary cholesterol effect is for most people pretty small, although it can be high in some high responders. Saturated fat, depending on how one produces the diet, can be reduced beyond what people conventionally eat, which is in the range of maybe 12% of calories. If you go down to 6 or 7% of calories, you can reduce LDL. But for most people, it's less than 10% reduction. It's not a big reduction. I can't give you the exact numbers because it varies from different studies, but it's a relatively small effect that can be amplified by including some of the fibers we talked about, the soluble fibers in particular. And there's a diet that has been developed that can reduce LDL by as much as 20%. Using those principles, which begins to be in the range when it can achieve in statins. But as I mentioned, the more potent statins can reduce LDL even further. 40,
so in general, diet has quite a modest effect on cholesterol levels. But one way you can lower them is to reduce saturated fat intake in addition to getting soluble fiber.
Yes, those are two dietary approaches that can lower LDL. I mean, certainly for people that have LDL levels that may be due to underlying genetic predisposition, they nevertheless may be responsive to these dietary changes. In fact, they often are, and we can sometimes bring the levels down. Having said that, I'll say one more thing about the diet, and that is related to the dietary guidelines issue we discussed earlier. Saturated fat has most of its effect on large LDL particles. It has, for most people, a very small effect on the little guys, on the small LDL. So when one conversely lowers LDL by saturated fat reduction, we published this a couple of years ago, as well as previously, one lowers the large LDL, but has relatively minimal effects on the small LDL. So that gets back to one of the reasons to support what we talked about earlier, trying to connect saturated fat to heart disease risk by simply looking at LDL may overestimate the benefit because the major effect is on the particles that have a smaller effect on risk, and we're not affecting the particles that are so prevalent in the population now that have a greater effect. These very small guys are really very minimally responsive to saturated fat. So the dietary effect varies across the spectrum of LDL. It also varies across individuals, in part due to their genetic nature. So it's another complicated question. I mentioned earlier a moment ago that people that are obese, interestingly, don't respond to saturated fat. They make enough of their own saturated fat. The dietary effect has relatively minimal consequences. So that's it. Diet and genetics, and then adiposity, as I mentioned, can raise LDL, but it raises the small LDL. So lowering body weight is effective in lowering small LDL particles. It can also affect the larger ones, but less prominently. And there are these other components I mentioned in the diet beyond saturated fat and cholesterol. People always ask me, can stress be a factor? The answer is yes, but it's very hard to quantitate, and it's usually if there is an effect, it's not enough to really enter into a formula to predict cardiovascular outcomes. That's about it for the causes of cholesterol elevations in the population.
When we talk about HDL cholesterol versus LDL cholesterol, these are commonly referred to respectively as good and bad cholesterol. Is that a useful shorthand to refer to these? Do you think we should be using those terms? Is it really as simple as one's good and one's bad, so you should want higher levels of one and lower levels of the other one? How much more nuance is actually there when we talk about good and bad cholesterol?
Well, I'll tell you, every question you've asked so far is a question that has a very extensive set of answers, and I'll try to be careful about not making it too difficult to follow. In terms of the LDL and the bad cholesterol, we just reviewed. Actually, one of the concerns I have is talking about LDL cholesterol. The cholesterol kind of LDL does not give an indication of the small LDL particles, for example. It's weakly correlated with the particle distribution, and therefore it's somewhat flawed. It also includes another category of lipoproteins that we didn't mention for the aficionados who may be listening to this. I just mentioned there's a category called remnant lipoprotein cholesterol. So we have LDL, which is the low-density lipoproteins. And then we have these remnant particles, which are actually even larger. They're actually larger than the large LDL, but they are derived from breakdown of other particles called VLDL, very low-density lipoproteins that start off in the liver containing triglyceride as well as cholesterol. And as they're metabolized, as the triglyceride gets lost, they produce these remnants. These remnants are highly atherogenic. So we have within the LDL spectrum differences across large versus small LDL, but LDL cholesterol also, the standard clinical measurement also includes remnant cholesterol. So one of the reasons, and I think one of the major reasons that LDL cholesterol has been pinpointed as bad cholesterol is because it includes these other components. It's not some simple single entity. Calling it good cholesterol, calling it bad cholesterol as a generic term is really, for that reason, oversimplification, but it's at least in the right direction. I mean, this is higher risk. When it comes to HDL, HDL also contains cholesterol. It's a smaller particle, has less cholesterol than LDL, in most individuals at least. And its levels have been very strongly related inversely to heart disease risk, such that people that are walking around with high HDL levels tend to have lower heart disease risk than individuals who have low levels of HDL, and there's cut points where below which HDL reduction appears to be quite harmful for many people. There's genetic reasons for that. It can also be lowered if you're overweight in certain, again, to varying degrees across the population, but obesity contributes to low HDL, and that is correlated with higher heart disease risk. However, there have been two categories of research that have challenged the assumption that changing HDL in either direction would affect heart disease risk. One is genetic, and that is that as opposed to genes that affect LDL that we talked about a few minutes ago, the genes that specifically affect HDL, the collection of genetic effects in HDL, have not been shown to be correlated with heart disease risk. So people carrying genetic traits that, for example, raise HDL do not appear to be at lower heart disease risk as a result of those genes. So that's one line of evidence which has been used to challenge the assumption that if you have low HDL, raising HDL would be beneficial. And there's a whole other category of data that supports that conclusion. And this is based on trials, particularly involving a vitamin called niacin or nicotinic acid. It's been known for decades to lower cholesterol, but also increases HDL levels, can increase HDL levels quite substantially. We can discuss these trials in more detail, but the bottom line is that the effect on HDL of those trials involving niacin could not be connected to lower heart disease risk as well. So that has sort of challenged the assumption that simply having a correlation of HDL with heart disease risk, which does exist, doesn't really guarantee that something that changes HDL is going to have the predicted effect. That argument, by the way, also applies to LDL. And it's another one of the arguments I've used to challenge the assumption that, well, we know LDL is related to heart disease risk. We know statins can reduce LDL and reduce heart disease risk. But do we know that the dietary effect on LDL is beneficial? There have not been studies that have really focused on that, as I discussed earlier. There was a large trial, and I'm going to go back now to one other line of evidence on the LDL side, where a large population of women, what was called Women's Health Initiative, were treated or were advised to follow a diet that was lower in saturated total fat and higher in carb. And at the end, there was really no significant impact on heart disease risk of that diet. So one can't infer from the relationships that we know for LDL and HDL as being, quote, good and bad, that changing them in any particular way is going to be beneficial. And that also depends on other effects of the diet. It goes back to the argument I was making earlier, the challenge saturated fat guideline. It really, you need to consider other effects of foods beyond cholesterol lowering. So do all saturated fats have that effect? And if you give me a minute to sort of sidetrack back to that topic, what I'll mention is that there is data to support that certain types of saturated fat, particularly those found in dairy foods, this is not my research, so I'm not conflicted by saying this, I don't think, are associated with improved cardiometabolic health, features that can predispose, for example, to diabetes and metabolic risk of heart disease that are benefited by the fatty acids, or that are associated, as I say, with benefits of these fatty acids. And so there is some evidence, which is the subject of some controversy and continual reevaluation, that the same amount of saturated fat, the total amount of saturated fat derived from dairy in particular, and other sources of saturated fat, non-dairy meat, tropical oils, have differing effects in heart disease risk, that the dairy context has other effects that go beyond cholesterol that can impact heart disease risk. So reducing dairy fat intake carries potentially the downside of pulling away those fats that might have beneficial effects. This is particularly related and particularly connected with another way that dairy products are consumed, and that is through fermented products such as yogurts and cheeses. And those fermented products, and particularly for the yogurts, have also been associated with cardiometabolic benefits. Again, these are cross-sectional, some interventional studies. And so, again, it points to the fact that simply labeling a product has slightly harmful effects due to LDL raising components, such as saturated fat, have they do not necessarily relate to heart disease risk. And then finally, getting back to that same arena of why I've been concerned about continuing to focus on saturated fat as the criterion for advising ways of reducing heart disease risk, the dietary guidelines, is that I mentioned, for example, that most of the cholesterol synthesis that we find in the body is produced by synthesis from tissues, including the liver. The same is true for saturated fatty acids. Most of the saturated fatty acids that circulate in our body are synthesized by the liver. It's by a process called de novo lipogenesis. And so while dietary saturated fatty acids can contribute to the body's pool of saturated fatty acids, for most individuals, and particularly those individuals who have these metabolic disturbances that are derived from excess adiposity, for example, what we call metabolic syndrome, who have insulin resistance and predisposed to diabetes, those very prevalent individuals, that large segment of the population, is actually producing a whole lot of saturated fatty acids from carbohydrates. It's the carbohydrates that drive this de novo lipogenesis process. And that just points the finger exactly at the opposite direction from reducing fat. It points the direct finger, again, at supporting the argument for reducing de novo lipogenesis. And fructose, which you talked about even earlier, as a specific sugar that drives some metabolic problems that lead to heart disease and diabetes. Fructose drives de novo lipogenesis, and that's been shown. Higher levels of fructose produce more of these saturated fatty acids. And here's where, like with cholesterol, what's circulating in the blood is not the same thing as what we consume. What's circulating in the blood is the endogenous saturated fatty acids. And once they're in the blood, they can be harmful. Saturated fatty acids do have harmful effects, but it's the circulating saturated fatty acids which are impacted more by, for most people, by carbohydrate than fat that drive this. And those effects can include both lipid synthesis, lipid metabolism, as well as inflammatory processes that can contribute to heart disease risk.
I see. So those, when we go back and think about those original guidelines that sort of made the inference from the data, which wasn't proven, that if you decrease saturated fat and replace that with carbohydrates, not only was the saturated fat decrease probably not having at least as big an effect as they hoped, but actually replacing those with carbohydrates was promoting lipogenesis and actually increasing circulating saturated fatty acids.
Right. And then that effect, again, if you have a diet that's extreme, which is low in saturated fat, high in polyunsaturated fat, and the carbohydrates are coming from healthy sources, plant-based, whole grain, et cetera, that effect would be minimized. But in practice, the way the guidelines impacted the population and the food industry, which really made the best effort to comply with those earlier guidelines that promoted carbohydrated, expensive fat, included foods that really were driving endogenous saturated fat production and could have adverse effects. And other mechanisms as well.
When we think about the different classes of fatty acids, so saturated, monounsaturated, polyunsaturated, there's heterogeneity even within those categories. But if we think about them at that level, the degree of saturation is related to how easily they can become oxidized. Is that true?
Yes, that may not be always the important mechanism that affects the biological effects. However, the differences in the structure relate to metabolic control through enzymes that pull away hydrogen atoms and progressively make bonds change from saturated to unsaturated. When there's multiple unsaturated bonds within the chemical structure of a fatty acid, it does become more readily oxidizable. That may have mixed effects. It may not necessarily, that form of oxidation, it's not clear, has adverse. Some people feel that it's an adverse effect. It's not clear to me that that's significant enough to warrant concern. Again, this topic is so complicated. I don't want to make it overly complicated. But within polyunsaturated fatty acids, There are two general categories which we didn't discuss. One is where there's a specific unsaturated bond in what's called the N-3 position. Those are called omega-3 fatty acids. And another, whether the first bond is in the 6th position, those are called omega-6 fatty acids. They're derived from different sources. Omega-3 fatty acids can be derived in the diet from flaxseed, but the form of omega-3 fatty acids that appears to have some metabolic benefits is mostly found in fatty fish who develop high levels of these omega-3 fatty acids. And that's been the source of many studies trying to relate those fatty acids to benefits, including heart disease risk reduction. Those are complicated by the fact that some studies have shown benefit, but more recent studies have not. So that's still an area of some controversy. That's as opposed to the omega-6 fatty acids, which are the major source of polyunsaturated fat in the diet, coming from seeds and nuts and various oils that have these effects, including association with lower heart disease risk, as well as lowering cholesterol levels. So that's just another element of heterogeneity that segregates these two forms of unsaturated fatty acids.
When you get omega-6s from whole foods like nuts and things like this that are unprocessed and have the fatty acids intact, do those omega-6s have a different effect compared to if you cook them with them at high temperatures in the form of, say, a vegetable oil?
Yeah, well, this is a topic that I have been exposed to by interacting and even publishing with colleagues who have made the point that that type of processing can have adverse effects on the structure of these that could be detrimental. I personally, accept the arguments to some extent. I just don't know personally whether I feel that this is enough of a factor that should cause people to avoid, perhaps, taking them after high temperatures. But this is not my area of expertise, and I've tried to avoid making any conclusions based on what I see as a very complex literature and a lot of controversy in this field. It occurs to me there's yet one other consideration regarding fatty acid heterogeneity, and that is what's called trans fatty acids. Trans fatty acids are distinguished from what are called cis fatty acids by having hydrogen atoms on both the top and the bottom of the structure, going in opposite directions from the main structure, whereas cis unsaturated fatty acids have those unsaturated hydrogen atoms sitting in the same direction. So what we see in practice is, or what has been shown in various studies, both interventional and observational, is a strong association of trans fatty acids with heart disease risk. And those are often found in highly processed fats that undergo high temperature, as you said, can generate these trans fatty acids from the way the oils are processed. And that is, I think, generally agreed upon as an adverse effect, which has led to changes in the food industry and the restaurant industry that have greatly limited the amount of unsaturated fat that we're exposed to, even to the point of putting this in the food label and making conclusions based on whether they meet a certain criterion for having unmeasurable amounts of trans fat. That's another important type of heterogeneity of fatty acids that could be considered in heart disease risk assessment. Having said that, believe it or not, there's even heterogeneity among the trans fatty acids. There's different forms of trans fatty acids, and not all of them necessarily have the same effect. So it really gets complicated. Mm-hmm. But again, in terms of trying to simplify the categorization, we have this sort of broad category of saturated fat. We have the broad category of monounsaturated fat, which is, for example, olive oil. We didn't talk about that. Canola oil is another one that has one of these double bonds in the structure. Then we have polyunsaturated fat. We have omega-6, omega-3. Then we have trans fat versus the normal cis form. and we have heterogeneity within each of those categories. So there we've got the full plate, if you will, of characters in this game.
In general, just directionally speaking, in general, for the United States, how have dietary fat patterns of intake changed over time? Are we getting more polyunsaturated today than we used to? Are we getting less saturated fat? What would have been some of the major patterns there, say, over the last 100 years?
Well, I don't have enough of a handle on that time span to give you exact numbers, but I can tell you that one of the consequences, and we think it's due to the guideline process over the last several decades, has been a reduction in the average consumption of saturated fat. And I can throw out some numbers, which I'm not going to stand behind because I don't have them in front of me, nor do I have the exact figures, but something in the range of 14, 15% of calories of saturated fat was not uncommon in the old days, and even higher in many cases. The average consumption has now been reduced to something between 11 and 12%. Saturated fat intake has come down, and some people think that that's a beneficial consequence of the guidelines, and I can't argue against that. I mean, I think that may be part of the reason why cholesterol levels in the population are dropping somewhat because of that. But we'd expect it to be a relatively small effect, but it's in the right direction. At the same time, we've had this corollary of reducing total fat and increasing carbohydrate at the expense of fat. And that has changed. And I can't give you the exact numbers there, but for example, just throwing some numbers out, which I can't be exactly sure of, something like half of total calories, 50% or so, or more, were coming from carbohydrates, or less, I should say. It started off in the old days, and I don't know if it's 100 years or 80 years or whatever, but carbohydrate intake was maybe 45 to 50% in general. The guidelines push that up to 50+%. So the guidelines push the carbohydrates in the other direction. Where we are now, I don't have the exact numbers, but we're not at the 45% level. And for example, from a metabolic standpoint, my own studies and those of others have suggested that we probably should go back to 45 or less as a target to try to reduce some of the metabolic adverse effects of carbohydrates overall, because it's not just sugars, it's all of these processed starches and carbohydrates in particular that contribute to that 50+%. And so I haven't answered your question in detail, but it's this general trend that we think has resulted, in part, at least, from the dietary guidelines that have been promoted and the food industry's efforts to meet those guidelines.
In one of the papers of yours that I looked at, and you mentioned something earlier. I asked you about the macronutrient composition of your breakfast, I think, and you said you don't think about things in terms of hitting specific numbers for yourself. And I know that you've written about something called the food and diet matrix. So what is this?
So that's considering the effect of the foods as we actually eat them. Which contain these chemicals. They contain the fatty acids, they contain the sugars and starches, but they are contained within what we call a food matrix. And I touched on one example of that in the case of fruits, where we see that the sugars in particular can be embedded in a food that has a lot of fiber that embraces the sugar and affects its metabolism. So that food context of a whole fruit versus a processed juice, for example, is maybe an extreme example of the food matrix affecting its metabolic effects. In the case of fats, there's studies which also point to the matrix as being important. I mentioned the fermentation process, for example, which appears to generate beneficial changes in carbohydrate quality that have been associated with cardiometabolic risk benefit. But in the case of cheese, it's been shown, and this varies across different cheeses, of course, but in general, the same amount of saturated fat in cheese has a much smaller effect on LDL cholesterol than the effect of that same amount of saturated fat in butter. So there's a few studies showing that saturated fat, while saturated fat may be equivalent across those two forms of dairy, the context in which the saturated fat is consumed within cheese due to something about the matrix appears to change its metabolic impact and probably its effect on heart disease risk. So that's the food matrix angle, which has really not been well enough studied in my view, and certainly not enough to be able to point to ways of assessing that analytically that could be translated to dietary guidelines.
Mm-hmm. Yeah, so I would imagine in general here, just to help people think about it, right? If scientists study the effect of like an isolated macronutrient on the body, it may or may not have the same effect in the context of whole food A versus whole food B, because there's just so many interacting pieces here that affect how each of the components is absorbed and used by the body. Is that basically it?
Well, that's a big part of it, but there's two other things to consider. One is the effect of other components in that same food that could be influencing the effects that have nothing to do with either the matrix or the nutrient of interest, that just sort of coming along for the ride. And particularly for plants, for example, there's just, I don't know, dozens or hundreds of what are called phytochemicals that are contained within fruits and vegetables that we can measure some of them, but we don't have specific evidence that one or another of those nutrients has an effect. So that's kind of a second axis by which the food context could have a unexpected effect, either good or bad, that would not be predicted from a particular component of the food. And then the third thing, the final thing that supports a concern about food context is not just the foods, but the overall dietary pattern. Because we can study individual foods, perhaps, but what we really consume is dietary patterns. We consume foods with other foods. We consume classes of foods together in some cases and not in others. And so there's the context, not just of the food matrix, but the overall dietary pattern. So I'm glad to say that the guidelines advisory group, at least, and I think the guidelines themselves have been certainly in the last edition, and hopefully in the future editions, will emphasize the role of dietary patterns overall, that exceed the information that we can get from trying to put numbers around the individual components and their percent of the diet. The overall dietary pattern should be considered as a major goal. And there have been studies, for example, involving what's called the Mediterranean dietary pattern, which itself has different versions depending on where you are in the Mediterranean world. But in that program, which is again, a number of different dietary effects that go well beyond effects on cholesterol, has been associated with improved heart disease risk as well as other metabolic benefits. And that's been promoted as one of the ways of achieving a healthy dietary pattern. But again, we really would really benefit from having much more data to support this and tell people exactly how they should be implementing these diets, because they don't always go to the literature and see what the studies were using. They need to get guidance that's much more specific, and we don't have enough data yet in that direction to really document benefits.
Well, Dr. Krauss, we've covered quite a bit so far. We've only got a few minutes left. Are there any final thoughts you want to leave people with about anything that we've talked about, the general subject of diet and metabolic and cardiovascular health?
Okay, so one can step back, maybe at the 20,000 foot level, if not the 30,000 foot level, and say that there are certain aspects of diet and cardiovascular health in particular that I think we can stand behind based on evidence that I mentioned that is not always perfect, not always sufficient to show causality, but which is sufficiently compelling to generate some healthful overall dietary patterns. And I mentioned the Mediterranean diet, but within that diet, I think there is evidence to support overall benefits, and again, not through mechanisms that we fully understand, of a variety of vegetables and fruits and plant-based foods and healthy carbohydrate foods that are not processed carbohydrates, that those plant-derived foods should be, and a variety of them should be consumed. I think goes beyond the cholesterol issue. It goes beyond being able to point to a specific component yet and say that's what you should be doing. It's really related to the overall dietary pattern, and that I think should be considered as a goal in one form or another to try to achieve. And I'll mention that one of our own studies where we looked at the effects of dietary protein. We didn't talk about dietary protein. I'll just throw that in since we didn't discuss that. There's been issues regarding is red meat worse than white meat, and how did that compare with non-meat sources? We actually did a study where we looked at not heart disease. It was not that kind of a study, but we looked at the LDL and other lipid levels, and we found that if one consumed non-meat protein as a major source of protein, that there was a lower level of LDL than with either the high meat or the high white meat or the high red meat diet. I mean, from either mostly from fowl versus beef and other sources. Their LDL levels were similar and higher than on the plant-based diet. So that gives us one other axis to think about, and that is the source of protein. And along those lines, I should probably also come back to one other issue we talked about, and that is the omega-3 fatty acids, which, as I mentioned, are enriched in fatty fish such as salmon, certain tunas, sardines, herring are all rich in these long-chain omega-3 fatty acids. There's some evidence, and again, it's observational evidence for the most part, that has linked in high intake of those sources of omega-3 with improved cardiometabolic and overall heart health that have not been necessarily reproduced by the fish oil themselves, not necessarily by the omega-3 component, but the food. This gets back in part to the food context issue we just discussed. So I'm in favor, in addition to having this overall balanced diet with plenty of plant-based protein sources, diets that include at least one or two portions of fish a week to provide whatever benefit that might provide, and then choosing carbohydrates that are unprocessed. And I tell my patients that consult me. Again, I talked about my cereal, my fiber cereal, which has a very high fiber content. One should look at the label of foods and look at the fiber content, look at the sugar content, and limit the sugar and try to, in the case of these carbohydrates, maximize the fiber intake. So those categories, I think, are major kind of bottom line dietary recommendations, which are more global and more general. And what's been shown is if one follows dietary patterns like that, including even the Mediterranean diet, one can back generate the percent distribution of calories. So you can learn what are those diets giving us if one's interested. And it turns out they pretty much conform to what we try to recommend. It's not having too much carbohydrate, not having too much saturated fat for many people. All of that sort of comes out in the end, but it's not necessarily the criteria. I don't think it should be the criterion, nor should it be considered the mechanism for benefit of those diets. It's really a marker of intake, but the real effect of these diets is coming from the foods and the dietary patterns in which they're consumed.
All right, Dr. Ronald Krauss, thank you for your time.
Okay, very good talking to you.
Hey everyone, I want to take a minute to tell you about a really cool health monitoring device I've been using for several weeks. It's called Lumen, and it's a handheld, pocket-sized device with a sleek design. It measures CO2 levels in your breath, which allows their technology to determine the extent to which your body is burning fats versus carbohydrates. Lumen helps improve your metabolic flexibility, your body's efficiency in shifting between using fats and carbs. It improves your ability to burn fat, which decreases your hunger levels and makes your body less dependent on snacking, and it can increase your energy levels by helping you develop a high-functioning metabolism. I use this device in the morning, before bed, and after meals and workouts to track my metabolism. With just a couple weeks of use, I learned a lot about which foods were causing my body to burn mostly fat, mostly carbs, or both, as well as how long I need to fast each day to promote fat burning. Lumen is great for anyone looking to optimize their health for either weight loss or athletic performance. The easy-to-use app allows you to track your results together with what you're eating and how you're exercising, and it syncs with other devices like the Apple Watch. Click the link in the episode description to learn more and use the code MIND, M-I-N-D, in all capital letters to get $50 off your Lumen device today.